Tcon to control the timers. Okay, so in the Tmod register, you've got 4 bits associated with each timer. 2 bits determine the mode itself. 1 bit determines the source of the clock pulses, which is the CT bit. C stands for count, T stands for timer. If it's low, it functions as a timer and it uses the on-chip oscillator to generate the pulses. If you set that bit high, basically it listens to a pin from the outside world, and it's, if you like, the pulses that come in on that pin that determine the count, which is exactly what we've got in this particular example here. This is so you can see in this particular case, pin 14 is actually the external input for timer 0, and pin 15 the external input for timer 1. For those observant members of you, pin 14 and pin 15 are actually 2 pins that belong to port 3. So if you wanted to use those 2 pins on port 3 for doing other things, you can't if you're using them to do this job. And it's only those 2 pins that you can use to basically drive the 2 timer counters. They're internally wired to those particular timer counters. So we have an example here where I don't know which one we're going to be using. Let's say if it's T0, pin 14. Effectively, we've got something that's generating pulses coming in, and that information is going into this timer, timer 0. And in this particular example, we've configured timer 0 for 8-bit auto reload. Remember, there are 4 modes of operation. 2 of them you're expected to know a lot about. The other 2, just about a couple of words is enough. Mode 0 we don't use very often. That's the 13-bit timer mode or counter mode. Don't use that very often. It's just for legacy. So you don't need to know any details of that one. Mode 1 is using it as a standard 16-bit timer or counter. In mode 1, when it overflows, it will wrap around and start counting from all zeros. If you don't want it to start counting from all zeros, when it overflows, it's your job to stop the count and to overwrite the information in the timer with the values that you do want. So you have to reinitialize the contents of the timer to the appropriate value. Mode 2 is 8-bit auto reload mode, which is what we're using here, where we only use half of the timer as a timer, effectively 8 bits, and the other 8 bits hold the reload value. The overflow happens when the lower 8 bits goes from FF to 00. At that point in time, the timer flag will be set, and automatically what's in timer high, the upper 8 bits, will be overwrite what was in the lower half of the timer. So you don't have to do that yourself. If you're using the timers as I've described so far, where we're not making use of interrupts, when a timer overflow takes place, it is your job, the person that wrote the program, to make sure you clear the flag. It doesn't happen automatically. Okay, so there's an example up here where we've got some kind of conveyor belt, and each time there's a package of pills going along this conveyor belt, a pulse is feeding into here, and we want to count, if you like, blocks of 256 packages. And as we're counting them, we're using port 2 to give some kind of display. And that's it. Not a very exciting example, but anyway, that describes what we're trying to achieve. And then yesterday, we briefly started going through the code for it. So just to recap that, the top line is configuring the Tmod register appropriate for our needs. Now actually I've got it wrong here. because I talked about timer 0, it's clear from looking up there, we're using timer 1 to achieve this. Okay? As you can see, it's all zeros down here. Now, I suppose you could be using it in mode 0, but anyway, knowing what we know about how we need to configure it, this bit and this bit select the mode, and that's set to the binary value 2. And this bit is the CT bit, which is now high, which says we want to use an external pin as the source of clock pulses, i.e. we want to use it as a counter. This bit here is the gate bit that normally we have low. The gate bit we only make go high when we want to use an external pin to basically suspend the count under our control, to pause things. So that's configured the timer, but at this point in time nothing's going to happen. This is loading the initial value into the high part of the timer, because remember it's 8-bit auto reload we've asked for. Now we've chosen to have a reload value of 0. So it's going to count from 0 all the way up to 255, and then when it counts to 256, what will happen is the overflow flag will be set, and as if by magic it will go to 0. Now you could say, well, why bother? Because in this case it's going to wrap around to 0 anyway. Good question, I don't know why, I didn't write the program. But this could be a value other than 0 here. If you wanted to count, for example, 16 packages before doing a reload, what you would do here is take 16 away from 0, if you like. You don't write the number 16 because it will count from 16 all the way up until it overflows. So if you want to count blocks of 16 packages, effectively you're basically saying, well, it'll overflow when it goes from FF to 0. You've got to work back 16 steps from that point. Now, you can work it out by hand. I didn't bring my calculator today, so I'm not going to dare attempt doing it in my head, though it's probably something obvious. Or you can let the assembler work out what the value is that you need. It's perfectly legitimate to do this, to say move timer high 1, for example, immediately minus 16 decimal. And it will substitute in here what is the appropriate value that's 16 less than 0. If you were asked something like an exam, that's perfectly legitimate to do things that way. Okay. Anyway, so we've loaded an initial value into the high timer here, and in this particular case we've set a bit. Now the reason why we're setting this bit I talked about yesterday is because this is the bit, pin 3.5, that's going to be used bringing in the pulses. Now it could have previously been used for some other purpose as an output. If it's previously been used as an output and we were to connect a 0 to that pin, now it's an input, we could destroy the transistor. So before we're actually going to make use of it as an input, the programmers decided to play safe and to make sure the transistor's switched off. So this is basically switching off the transistor associated with that particular port pin. If that doesn't make any sense to you whatsoever, don't worry, because we will be doing about this sort of bidirectional ports, how they're configured again in a week or two's time. Okay. But the rule of thumb is if you're going to use any pins as inputs, the standard practice is to write 1s to those pins which are going to be inputs before you start fiddling around with them. Having done that, we've effectively pretty much initialized everything, and then at this point here we've switched on the timer itself. You'll notice that TCON is a register that's bit addressable. So I haven't had to write a whole byte to the TCON register. I can actually talk to individual bits. You can't do that with the TMOD register. The TMOD register, you have to write a whole byte at the same time. It's not bit addressable. So we've started the timer off, and then we're just kind of going around here. So we're taking the contents in the low part of the timer, writing it into A, and then copying it onto port 2. This is just for display purposes. We just want to know what the current count is. So we keep doing that, not very exciting. So you keep doing that, going round and round here, just copying what's in the counter and writing it out onto port 2. All the time, though, we're monitoring this flag, TF flag. Has it overflowed? Now, it will overflow when it gets from FF to 00, which should be 256 pulses later, i.e. 256 packages of pills, and I don't know what kind of pills they are. Having got to that, you've counted your 256, you want to basically do something else, I don't know, send them over, change the direction of the conveyor belt or something. It's not made clear. So we're stopping the timer at this point in time and clearing the flag. We've counted our block of 256. If we forget to clear the flag, then when we come back in here, we'll have thought we'd counted 256 again when we haven't. So we must manually clear this flag, and then we're just jumping back here and then going through the next block of 256 packages of pills. Okay. Let's move on. Right, I haven't shown you the TCON register in detail. In the context of an exam, I would suggest that the TMOD register, you need to know what it looks like. So of the registers we've done so far, the registers I would say you need to know what they look like is the program status word and the TMOD register. There'll be a couple of others that will be coming across over the next few weeks. The TCON register, you'd be expected to know what's in it, but not necessarily be able to put the bits in the right places. As far as we're concerned, we're only interested in the upper half of the TCON register. The lower half of the TCON register is all to do with interrupts. And we haven't done that yet, so we can ignore that for now. And it doesn't have anything exciting in it. There's the, if you like, the thing to get timer 1 to run, thing to get timer 0 to run, and the 2 overflow flags. And that's it. I've mentioned about gate before. Even though you've set TR to be high to make the timer run, if you've set the gate pulse to be high, you can use one of the pins external to the 8051 to suspend the count. Okay? So it can act as a kind of pause. If I whiz back, you can see that even though this is high, and remember, if it's high, effectively this would pull this down and close it. If gate's high, this is coming in low here, and then that's an OR gate, remember? The status of this pin will determine whether the output of here is high or low, and of course if it's low, this AND gate output will be forced low, and so even though TR is high, it won't have an effect. So when gate is high, this pin becomes significant and can be used to suspend the count. Oops, going the wrong way now. Oops. And that's okay. Any general questions about timers? We've done it. Didn't take long, did it? We're going to move on to interrupts next, but if you've got any quick questions, I'll take them. No. Okay, good. I think I'll say something general about interrupts first of all, and then we can go through the slides. Let's say that you have a program you're driving a car, and it's not a very exciting car because it just has a, well, let's say it's just got a brake pedal. It's freewheeling down a hill or something, I don't know. And the brake pedal happens to be a binary brake pedal, it's either on or off. Let's keep it really simple. And you've got a little bit of software that's monitoring the status of this brake pedal. So far, the way that you would have learnt in this course to test this is to basically look to see, has the brake pedal been set? So you observe it, and then, now let's say you might have another thing to do. Let's give it something else. Can't think of something else to do. Let's say there's a switch to do the lights. So this car has lights as well. It's getting advanced now. So it's got two things it needs to do. It's got two switches. There's one switch that controls the lights and another switch that controls the brake pedal. You could write some software where you check the switch for the lights. Has it been high or low, whatever? If it has, do something. If not, check the brake pedal. Has it been pressed or not? If not, you know, and you keep going backwards, going round a loop, checking these things. So you're kind of doing check lights, check brake. And you've put this inside a loop, so it just does this forever. For some circumstances, that's perfectly okay. But if I was buying this car, I probably would be a little bit concerned if that's how the software system had been developed to control this car. Because what happens if I happen to be in the process of checking the lights or doing something with the lights bits, and then, I don't know, a little cat runs out in front of my car, and I want to stop, you know, I like cats, so I don't want to get squished. But I'm checking the lights. Well, poor cat's going to turn out into goo, and it's not going to work very well. So, there is a way around this, and this is what we consider an an asynchronous event, if you like. It's something you don't know when it's going to happen. It's not a regular thing, but what you'd really like to be able to do is, if something unforeseen happened like this, to be able to suspend what you're doing and deal with this important emergency. So we could rewrite our program where we did something like this, check lights. Not an exciting program now. And then something could automatically tell us that something's happened to the brake. So the main program, the thing that maybe checking lights and doing other things, can be interrupted. It can be paused in order for you to go and do something that's urgent. So the concept of an interrupt is, under hardware control, you're able to stop the flow of the program, to suspend it, and to basically effectively start a new program in order to deal with the source of the interrupt. The 8051 and any kind of microprocessor that has an interrupt capability, it's basically implemented within hardware. Okay. So, not all processors provide interrupts, by the way, because one of the difficult things about this is you don't know when it's going to happen. And there are some, if you like, ultra-safe systems out there where they don't like to use interrupts because if you've got a big program and it could be interrupted at any point within that program, it's hard to be sure that the behavior is going to be correct. But anyway, let's put that to one side. The 8051 supports interrupts. Okay? So in the 8051, what you can do is, well, let's think about these sources of interrupts. In fact, in the 8051, there are 5 main sources of interrupts available to you. So this is inside the 8051. The first one is, if you like, a special external input. And I'll call that int 0. So if you choose to configure it to enable it, if a particular pin on the 8051, here's an 8051, one of these pins that come into it if you make it go low, it will trigger an interrupt. The next one, and I'm writing these in a particular order, is timer 0 overflow. So we've been doing lots of stuff with timers, and so far we've been having to check that TF flag to see if it's gone high. It's possible to run the timer, and when the TF flag overflows, it will stop doing whatever it was doing and immediately deal with the overflow. Next one, external input 1. That's int 1. So that's another one over here. Next one, not surprisingly, timer 1 overflow. And then finally, the serial interface. I haven't said much about the serial interface yet. The serial interface is connected to 2 pins on the 8051. You've got a pin called RXD for data that's coming into the 8051 and a pin called TXD for data that's going out. If I draw it down here in a little bit more detail, you've got RXD coming in, TXD going out, and these are both connected to a special register called SBUF. There's, on this side of it, for things going out, there's a flag called TI, transmit interrupt, and on things on the input side, there's a flag called RI.
How many bits is SBUF?
How many bits is the buffer?
Yeah.
It's 8 bits. So you can, well, it can be 8 or 9 bits, but usually 8 bits. So what would normally happen is you write to SBUF, it will automatically go into here, and things will be transmitted. As soon as you write into here, it starts to get transmitted. When the transmission is complete, this flag will go high. If anyone talks to you, it will automatically be stored in this buffer, and when the whole frame of information has arrived, all 8 bits or whatever, this flag will go high. Both of these flags are kind of tied together to generate the same interrupt, a serial interface interrupt. So if a serial interface interrupt happens, you're actually not quite sure what's happened. Is it because you've sent something out and it's finished, or is it because something's arrived and it's finished? So what you would have to do in this case is you would have to interrogate these flags to find out what was the cause of the interrupt. Is it because I've finished transmission, or because something fresh has arrived and I need to read it? So inside 8051, there are 5 sources of interrupt. 2 of them are linked to timers, and 2 of them are linked to external pins for sources of external interrupt. Right, I'm going to talk a little bit more now about what actually happens when we have an interrupt. I'm kind of racing ahead with the slides here, but I just want to give you an overview, and then we'll work through in a little bit more detail what's on each of the slides. Inside the 8051, you know, I should spell it the American way. You know there's a type of memory called program memory, code memory. There is also data memory, yeah? Okay, we've got data memory over here. The data memory is that, if you like, 128 bytes of things that include things like the register banks, bit addressable, general purpose, and then above that, we've got the special function registers. Elsewhere, we have this other type of memory where we have our program. Technically, by the way, there is one more special type of interrupt, but I'll come on to that in a minute. Program memory starts from location 0000, and the program generally works upwards from that point. Okay? And so far, we've just been writing programs starting at 000 and kind of working up. However, if an interrupt was to happen, the program counter will be updated, and the program counter will point to a specific location in the program memory. You cannot change that value. Intel have decided, depending on the type of interrupt, where the program counter will point to. So there are special locations within the program memory that if an interrupt happens, the program counter will point to, and you will continue executing your code from that point onwards. Now, I don't remember all of them, but one of them, for example, is at location 0003. There's another one that's at location 00B, and so on. Now, I can't remember which one it is associated with 03, but if that source of interrupt happened, what would happen is you might be up here, somewhere in your program, running your code. The program counter's pointing to the next instruction that you need to run. When the interrupt happens, a whole chain of events take place. One of the things is first thing is current instruction completes. Number two, PC stored on stack. Point three, current interrupt state is also stored. It's not stored on a stack, it's stored somewhere magical. Some special little hidden place. The reason why that's there is because it might be possible, in fact it is possible, that when you're dealing with one interrupt, the 8051 can be interrupted again by a more important interrupt. Yep.
What does interrupt state mean?
If you're currently in an interrupt, what you want to do is remind yourself that you're currently in an interrupt, so that when you finish doing the high priority thing, you don't go back to the main program, you go back to the interrupt that you were dealing with before. So this is important because, in fact, in 8051 there are two levels of interrupt that are supported. So there's the normal level of interrupt, and then you can have high priority interrupts. Now you're going to say, well, how do I, which is the high priority ones? All of these could be high priority, and all of them could be low priority. It's your job as the programmer to choose if you want to make any of these high priority. If something happens and an interrupt is enabled, you go and deal with that problem. You go to the special bit of code to do with it, and I'll talk you through this in a minute. However, while you're doing that, if another interrupt happens, and it happens to be higher priority than the interrupt you're currently dealing with, you can go and deal with the higher priority thing, and then come back to the low priority interrupt afterwards. Okay? There are only two levels of priority of interrupts in the 8051. So low priority and high priority. So, the sequence of actions, sequence. So, whatever you're doing, even if there's an interrupt, you don't stop halfway through an instruction. You complete doing whatever you're currently doing now. You finish that one instruction off. But at the end of that, the program counter is stored on the stack. You remember somewhere what the current state of the interrupts is at the time that you are here, because you could already be in an interrupt. Then you update